It's time to introduce the capacitor. I've drawn what is a very normal diagram for how a capacitor is produced. Typically, there are conductive plates here and there, and in between is something called a dielectric or non-conducting material. It's important that the non-conducting material is in between the two conductive plates. The reason is because when we apply a voltage across these two conducting plates, current cannot pass through. Now, you might think this is a relatively useless device then. Wouldn't this just stop the current from flowing and therefore the actual circuit wouldn't do anything? Something very interesting happens when the voltage is applied across the plates. Imagine an electron going through to the plate. Because voltage accelerates electrons, it'll keep on moving, assuming that there is some wire here, until eventually it stops on the plate. It can't pass through. Electrons accumulate all along the plate. This plate then builds up negative charges. If there's an excess of negative charge, they'll start pushing electrons off of the other plate, and this plate builds up positive charges. What we end up with then is a voltage difference between the two plates, and this flow of electrons is the current that continues. In fact, sometimes you'll hear it as the continuation current. The key idea here is that now that there's a difference in charge between the two plates, there's actually this voltage between them. The energy is stored because there's a difference in charge between the two plates. Since charge accumulates on the capacitor, we can actually quantify it, we can measure charge, and it turns out that charge is actually proportional to the voltage between the two plates. A proportionality constant is the capacitance. The unit is the farad, named after Michael Faraday, who studied capacitors significantly. 1 farad is equal to 1 coulomb per volt. What this means is that a capacitor with capacitance 1, if a voltage of 1 volt is given across the plates, a charge of 1 coulomb accumulates. Now, there's something very important to know. 1 farad is huge. It is a giant capacitor. Normally, we work in terms of picofarads, nanofarads, microfarads, and millifarads. It's relatively rare in most electronic devices to see anything approaching a 1 farad capacitor. However, in certain high energy applications, and other applications like, for example, a microwave, you might see something that large. Now, if Q is C times V is the accumulated charge, but remember, I said there was that continuation current. Well, we know that current is dq by dt, the derivative of the current with respect to time. So, dq by dt can also be given like this. Almost always, capacitance is constant. There are very few devices in which we have variable capacitors that change while we're analyzing them, but they do exist. Therefore, the current is actually C dV dt most of the time. And again, it is possible to have a variable capacitor, but normally we don't consider them. Now, how do we draw using the passive sign convention? There's something very important to know about these energy storage elements. Capacitors are passive devices. They are not sources. They do not contain the own source of energy. The energy comes from outside. Specifically, the source is in the circuit. Therefore, capacitors follow passive reference convention. Which means, if I draw my capacitor, this, by the way, is a circuit symbol, and these are my two terminals, and positive current is entering, then I labeled this terminal as positive and this one as negative. As with all passive devices, positive current enters the positive terminal. Finally, it's possible to compute the voltage as a function of time by integrating the current. And your textbook also says that we should consider the initial voltage on the capacitor. Usually, we will start at 0. But there are many different applications in which that wouldn't be true. In the next video, we'll talk about how to use capacitors in a circuit.